Hi everyone, in this video we are going to discuss the difference between temperature and heat. Now this is something that a lot of students struggle with because we have a misconception of what temperature means as we enter this course. But right now hopefully we can kind of solidify that and make sure that we understand exactly what temperature is and what heat is. So let's start off with temperature because that's the one we are most familiar with, probably. Temperature is simply a measure of the average kinetic energy. And so when I think of temperature, I think of it as very static. So it's something that is, you're measuring the kinetic energy at one specific moment in time. You're not actually measuring the transfer of energy. You're just measuring for this system, whatever your system is, at this specific time, what is the temperature. And so we measure temperature in Fahrenheit if you're from the US, but everybody else does degrees, Celsius, and Kelvin. So for this course, when we talk about temperature, I want Celsius or Kelvin. That's it. Never say Fahrenheit. I don't care about Fahrenheit. Now, heat. Heat is different. Heat is a measure of the transfer of kinetic energy. So now, what I mean by that is kinetic energy always moves from a hot object to a cold object. Always. You will never, ever, ever see cold go to hot. So let's get this down right now. Always hot to cold. Always. It's never going to be the opposite direction. So now we could describe this as unorganized molecular motion. So the reason we use this phrase is think about a pot of water, right? Okay, you have water, you start to heat it up, you're boiling it, let's say you're going to make pasta or something. As you turn up the heat, as you increase the heat and that water starts to boil, you're going to create a number of different water vapor molecules, essentially. So you're releasing water into the gaseous phase. But it is completely unorganized. It is chaotic. As soon as that water molecule turns in the gaseous state, it takes off and it just goes in whatever direction it feels like going. It's not like they all come together and go, okay, we're going to move to the left right now, or okay, we're going to move to the right. That's not how it works. It's unorganized. But all it matters is that you go from hot to cold. Now, heat is typically measured in joules. That's my personal favorite. Or sometimes you're going to use calories. So calories can be used as well. So those are your units, joules and calories. Now, heat is usually abbreviated by the letter Q. It is a lowercase q. It is not a capital Q. It is a lowercase q because that means it is not a state function, okay? Now, temperature is represented by a capital T. We use a capital T because temperature is a state function. All right, so now I'm talking about temperature and heat and giving you all the technical definitions, but why am I doing this? Well, we need to figure out a way to quantify heat energy. So how do we actually measure this? So how do we measure it? And the answer is with this really cool instrument called the calorimeter. So essentially what a calorimeter is, and I'm going to do this in the most basic form, is essentially a big box, okay? It's a big box, and inside the box we have a smaller box. Inside the smaller box, we have our sample. So this is our fossil fuel, this is our methane, our hydrogen, whatever it is that we're talking about, that's your sample. This is what we're going to set on fire. We're going to combust it. In here, we're going to do a combustion reaction and poof, explode this material, this sample, whatever it is. Now that's in its own little casing. Completely surrounding this is water. So I'm going to go all the way up to the top to kind of show that. But this whole piece all the way around here, this is all water. All of this, all the way around. Now what we do is we insert a thermometer into the water. So this is a thermometer, which is going to measure the kinetic energy, the average kinetic energy at a specific point in time. So what we do is we set the sample inside the little box and we measure the temperature of the water in the beginning. So we measure some initial temperature. Let's say it's 25 degrees Celsius. It's at room temperature. Now all of a sudden we do our combustion reaction. So we set it off and we go poosh, so we have this huge explosion. Well, the heat is transferred from the inside here out into the water. And so what we can measure on the outside, we're standing over here just measuring this reaction, we can watch the thermometer increase in temperature, or we can watch the thermometer measure the increase in temperature. So maybe it started at 25 degrees Celsius, but at the end of the experiment, it peaked at, let's just say, 40 degrees Celsius. And so what we can do is look at this change in temperature and convert it to a measurement to determine the amount of heat. Now, that can get very complicated, so we're not going to ask you to do that in this course. But what I need you to understand is there are two different types of calorimeters, and we have very specific conditions that we use to describe these calorimeters. So the first one here is a bomb calorimeter. This is referred to as a bomb calorimeter. Now, the condition we use for a bomb calorimeter is that it's at constant volume. So we're going to say if we ever use a bomb calorimeter, there's no way the volume of our instrument is ever going to change. And so here you can see our inside. So this is our sample is in here. That's actually our sample right there. We can see the water. That's our blue stuff. And then we see our thermometer right there that's measuring the temperature. Now we have the ignition wires. That's how we actually do the combustion reaction. We set it off. And then we have a stirrer. That is simply to just move the water so that the water doesn't stay in one spot and have maybe the spot right here get really hot. We want to make sure the whole temperature or all the water is at a uniform temperature. So that's a bomb calorimeter. Then we also have this one called a coffee cup. So a coffee cup calorimeter, oops, lots of E's in coffee. A coffee cup calorimeter is very simple. So this is something we would do in a general chemistry lab. So you literally take one coffee cup in styrofoam, put another coffee cup on top of it, cover with one cover, and then you can see that thermometer just goes right through the center and poosh, set it right in the middle. So what you do here is you put your sample right in. So your sample actually is interacting with the water here. It's not separate like in a bomb calorimeter, it's right there. So your sample's there, you set it on fire or whatever it is you're gonna do, you put the water in, you have a stirrer, and just like before, you measure the temperature using a thermometer. So for a coffee cup, we assume it's under the condition constant pressure. And so the reason we assume constant pressure is because this is just a plain old styrofoam coffee cup. So what we're going to be experiencing is atmospheric pressure, which is 1 atm, is coming down here constantly, and we're going to assume that we are always at a state of constant pressure. Okay? So now, let's talk about this in more, maybe a more specific example. So like, why are we doing this? Well, essentially we need to be able to come up and measure the amount of energy released with a combustion reaction. So we're trying to quantify the actual amount of energy released by doing this combustion reaction. So let's look at a specific example. Let's look at the combustion of natural gas. So we have methane plus oxygen going to carbon dioxide plus water. Now, if we're going to include a heat term in here or an energy term, we're just going to say plus 802.3 kilojoules, and this is always per 1 mole. So we see in front of this methane right here, there's a 1, so that's per 1 mole. And so I'm going to go ahead and balance this for you, but at this point in the course, I expect that you can do this already. So here is my question. Without doing any information, without calculating anything, without doing anything farther, is this an endo or exothermic reaction? What do you think? Endo or exo? Go. Did you get an answer? Hopefully you did, and this is definitely an exothermic reaction. Remember, the entire point of this unit or this module is to study the heat that's evolved by burning these fossil fuels. If a combustion reaction was not an exothermic reaction, we would not even be studying this stuff. We wouldn't care about it at all. So in your mind, you need to be thinking combustion reaction, exothermic, releases energy. So if you were to ever write it out in a chemical reaction or a chemical equation, if we're writing it out, remember the difference, we would put it on the product side, okay? If it was endothermic, it would be written, this number would be written on the reactant side. All right, so now let me ask you to take this a step further. How much energy is evolved upon the combustion of 5 moles of methane? Go. All right, did you get an answer? Hopefully you did, and all you had to do was some dimensional analysis. So the first thing we had to do is come back up here and look at that number. So we said that for every mole of methane, so for every 1 mole of methane, we release 802.3 kilojoules of energy. But now I'm trying to ask you to solve it for 5 moles. So let's just multiply this term times 5.0 moles of methane. Our moles are going to cancel out. We simply do 802 times 5, and if you do that properly, you should get an answer of about 4,011.3.5 kilojoules. That's your answer. Take care of yourselves. Drink water.